Okay, so let's recall that in the previous calculus video, we discussed about some points, some types of points at which a function is not differentiable. Among such points is also the type where a function is not continuous. So such points are called points of discontinuity, points in the domain of a function at which the function is not continuous. We saw graphically that at such points a function is also not differentiable, and the geometric equivalent statement of this fact is that if one draws the graph of such a function, then at a point of discontinuity there is no tangent. In fact, we saw two cases of this. One where the discontinuity is a jump discontinuity whose graph looked like this. One half of the graph is like this, and then it jumped from that value to a higher value and then it went down. And the other case is a removable discontinuity where the graph is like this. You may remember if I draw this. The graph is like this, from which a single point is missing. In place of that point, there is another isolated point which is also a part of the graph. At such a discontinuity also, the function is not differentiable. Geometrically, the graph has no tangent at that point. We have already seen this, and that in fact motivated this question: is it true always that if a function is discontinuous at a point, then it is also not differentiable at that point? Yes, it is true. Or in other words, for a function to be differentiable at a point, it is necessary that it also be continuous at that point. Continuity is a necessary condition for differentiability, and that's what we are going to prove today. So the statement is this: if f has a derivative at x equal to c, where c of course is a point, some point in the domain of f, then f also has to be continuous at c. So let's now see the proof. Actually, there are three cases depending on what type of point c is. One of those cases has been handled in the text, so we are also going to see that case. The other two cases I will discuss briefly about them, how to write a proof for them as well. So let's see the case that the text shows. And that case is this: let C be an interior point of the domain of f. The kind of domains that we are considering of functions, the domain of f of course is some interval. Now C being an interior point means that we have a little bit of area to the right of C and a little bit of area to the left of C within that interval. In other words, C is not an endpoint of the interval. C lies in between the endpoints somewhere. That's what it means for C to be an interior point. So it is given that this exists. The derivative of f at C exists. This means that this limit exists f of C plus h minus f of C divided by h, as h approaches 0, this limit exists and its value is f prime of c, this real number. Now, what do we have to prove? We have to prove that f is continuous at c. So, by definition of continuity, we have to prove this limit of the function as x tends to c should be equal to the value of the function at c. This is what we have to prove. Or equivalently, we have to prove this. Equivalently, we have to prove this limit. You can change the variable here. X approaching c is the same as c plus h approaching c as h approaches 0. Okay, it's because as h approaches 0, c plus h of course approaches c, and that's why in place of x you can write c plus h. And whenever we have or we are talking about a limit like this, we already know that from the definition of limit, the point towards which the independent variable goes, it never takes that point itself as its value. So what that means here in particular is that in this limit, h is not equal to 0. Here of course that's a necessity, that h cannot be 0, otherwise things will become meaningless. Here that is not a necessity, but that's what the definition says. A limit like this has nothing to do at the point h equal to 0. I mean, if you want, you can take h equal to 0 here, no problem will be there, but that has nothing to do with the limit. In fact, we have seen quite a few problems about this issue. So we can write like this: since h is not equal to 0, we have this. F of c plus h can now be modified like this. First of all, what I do, I add and subtract f of c. And then I multiply and divide by h, this term. I divide by h, and to compensate for that, I also multiply by h. Okay, now you see this. As h approaches 0, the limit of h itself of course exists, and it is in fact 0. As h approaches 0, the limit of this quotient also exists, and that is f prime of c. And this in fact is a constant. So as h approaches 0, this approaches itself, it does not change. In other words, all these functions have limits as h approaches 0. So from algebra of limits, this also will have a limit as h approaches 0. In fact, the result we are going to refer to here for this I mean, you will need it here. It is theorem 1 from section 1, 2. But before we do that though, will it be better if we write all those things? I think that's not necessary. You can simply write the theorem. So, by theorem 1 of section 1, 2, it's 1, 2 or 2, yeah, 1, 2, it's not 2, 1. This will be limit of f of c as h approaches 0 plus limit of this quotient as h approaches 0 multiplied by limit of h as h approaches 0 by algebra of limits, by this theorem 1 from section 1. Now this is constant, so it doesn't change with h, and so the limit is also the constant. This is the derivative of f at c, and this limit of course is 0. So we get c, which is what we wanted to get, and that is why f is continuous at c. At x equal to c. But this is only the case where c is an interior point. What if c is an end point of the interval on which f is defined? The text says that in that case the proof is similar and one just has to use one-sided limits. Let me just see one of the two cases, namely say c is a left endpoint of the domain of f. Next, let c be the left endpoint of the domain of f. Note that since we already are given that f is differentiable at c, so when we say that c is a left endpoint, this means that the domain of f looks like this, and on this side the right endpoint can be something which may or may not belong to the domain. But we know that the left hand side of the domain, left end of the domain looks like this, which means that the hypothesis that f is differentiable at c also has a slightly different meaning here than its usual meaning inside this domain. Inside means in the interior part, and the meaning is that here f prime of c is what? It won't be this limit, because now we no longer have a left side of c. There is left, I mean you have room to the left of c, but that's no longer a part of the domain of f. So this derivative is a one-sided derivative, it's a right derivative, because you can only consider points to the right of c even while calculating derivative. And that's why it is this one-sided limit. The difference quotient, of course, it won't change. It's still f of c plus h minus f of c divided by h. But this time, c plus h has to lie inside the domain. That means h is not allowed to be negative. If h becomes negative, c plus h will become less than c. It will come to that side. And on that side, there is no domain. We go outside the domain. So h has to approach 0 but from the right side. That's the difference. And also the conclusion that f is continuous at c means this thing. You have to show that the limit of f of x as x approaches c is still f of c, but when x approaches c from the right side of c. So here also you consider the right hand limit, because the left hand limit cannot be considered. So now shall we write the proof? It will be identical to that, only with these small differences. Let's just write it. And if c is the right end point of the domain of f, that case I will leave to you. Then, first of all, we write the derivative. H tends to 0 plus f of c plus h minus f of c divided by h is f prime of c. Depending on the type of c, we do not, however, have a different notation for this. We also write this as f prime c. Okay. We have to prove that f is continuous at c, which in this case means that the limit of the function, the right hand limit of the function at c is equal to the value of the function at c. So again same thing, since, okay, I did not write this in terms of h, no? Or equivalently, we have to show that this right hand limit at 0 of f of c plus h is f of c. Since, you see, in case c is an interior point, c was an interior point, we wrote since h is not equal to 0. Now also you can write h not equal to 0, but it's better to write what h really is. H in this case is a positive real number. So since h is greater than 0, I mean in this case also if you write h not equal to 0, that will work. But this shows that you are aware of the change in the situation right now. Okay, h is still non-zero, but more specifically h is positive. Via f of c plus h, writing c plus h like that is, there is no change, it's identical to what we did before, minus f of c. Now you will have to apply a result that is similar to theorem 1 of section 1.2, but which is for one-sided limits. You may remember about a remark that we gave after stating that theorem, and I think we proved a few parts of the theorem as well, not all of them. Okay. After having that proof, we made a remark that similar results are also true for one-sided limits. And I don't remember exactly, I think in the exercises, some such things have already been handled for one-sided limits. But anyway, we just simply straight away apply the result for one-sided limits. Hence, we don't even say anything. Hence, limit of f of c plus h, it's understood what we are doing as h approaches this time 0 from the right side. So this is equal to the right hand limit at 0 of f of c plus the right hand limit of this difference quotient times the right hand limit of h at 0. Again, this is going to be f of c, because whether h comes close to 0 from the right side or left side, it does not matter, or from both sides, f of c is not changing. Here also we get 0, and this of course is the right derivative of f at c. Okay, so in this case also f is continuous at x equal to c, which really means that f is right continuous at x equal to c. So now you can easily write the proof for the case where c is the right endpoint. And once you do that, then the proof will be complete. So that is left to you. Okay, now comes an interesting fact from this whole thing, which is given by the authors in the form of caution. The converse of theorem 1 is not true What does theorem 1 say? Theorem 1 says basically just this. If a function is differentiable at C, then it's also continuous at C. What will be the converse? The converse will be this. If a function is continuous at C, then it's also differentiable at C. No, that is not true. We already know one example at least of that. The absolute value function, whose graph is this, is continuous at 0, continuous at x equal to 0, but is not differentiable at x equal to 0. So, continuity at C is a necessary condition for differentiability. If you have differentiability, then you necessarily have continuity at that point. But it's not a sufficient condition for differentiability. continuity at C alone does not guarantee differentiability at C. So this is one such function. Now, how extreme can this example be? I mean, fine, this is continuous everywhere and not differentiable at one point. Elsewhere it is differentiable. Now, how extreme can this be made? Let's see. It can be made as extreme as it can possibly be made. Namely, there exist functions which are continuous at every real number but differentiable at no real number. Do you recall that while discussing the non-differentiability of the absolute value function at 0, we made the observation that it's because its graph has a sharp end at that point. That's why it fails to have a unique tangent at this point, which is why the function fails to be differentiable at that point. So from that point of view, in order for a function to be not differentiable at every point, the graph has to have sharp ends at every point. So how jagged should the graph be? Weierstrass found that yes, such functions exist, although you cannot draw the graph. In fact, he gave a class of such functions. But anyway, this is the thing. Karl Weierstrass. In his honor, let me just write the birth and death day of this great mathematician. So he was born on 31st October of 1815 and he died on 19th February. Of 1897. Karl Weierstrass found in 1872 a function, in fact, many such functions which is continuous everywhere in R but differentiable nowhere. See, thinking abstractly about functions is a little difficult. Whenever we want to have some behavior that we want a function to show, to exhibit, we normally think of its graph. So, do you see the apparent impossibility of thinking of a graph which is so jagged that at every point it has a sharp end? I mean, you can just imagine that, say, the graph looks like a coastline which is so irregular that it seems to be jagged at every point. No matter wherever you zoom in, you find jagged edges. Whatever point you zoom in on, that point is a corner of the graph like this. But you may imagine that on sufficient magnification, you will come across a point which is a corner point, but around it it's like this. No. For the functions that Weierstrass found, their graphs are so jagged that its graph cannot in fact be thought of. No matter how much you magnify, you keep on getting these sharp ends. The function becomes smooth in no region at all. It is because of this apparent geometric impossibility that people failed to see that such functions can even exist. And one example is this. Oh, I did not complete it, no, but differentiable nowhere in R. One such function is this. This is going to look very complicated, but you can imagine it won't be anything simple. It is given in the form of an infinite series . So the variable x appears here inside a cosine function. For every real number x, this series converges. In other words, to put it simply, you can find the sum and it will be a value. So it's a legitimate function. But it's a function which is continuous at every real number x, but differentiable at no real number x. Study of such functions is important in something called chaos theory. One of the reasons for that is that to curves which exhibit this type of behavior, which are extremely jagged, no possible finite length can be assigned, and apparently this is the fact that makes them useful in chaos theory. I also don't know in what sense what this thing is all about. Maybe someday I will learn. Okay. So I am also as much in the dark about this as you all are. That's what it makes these things fascinating. I mean, we cannot expect to know everything, but that is nothing to worry about. It means that we have more things to know. Okay. Now there is one more property of derivatives with which this section ends. That is the intermediate value property of derivatives. So next let's see this. Intermediate value property of derivatives. We already know about the intermediate value theorem, which says that if a function is continuous and takes two values at 2 points, then it also takes on the intermediate values. So such a property is also true for derivatives. And the proof of this, however, is not given in the text because it's somewhat too advanced for this level. Every fact that is mentioned at this level, you cannot expect to see the proof here itself. Do you remember that while we started our study of calculus from this book, in the very beginning, 3 types of properties of the real numbers were mentioned: algebraic properties, order properties, and completeness. Algebraic and order properties were discussed fully. Okay, we already in fact know about them. The algebraic properties say that the real numbers can be added, subtracted, multiplied, divided to give you more real numbers, and these operations are subject to the usual rules of algebra. The order properties give you properties of inequalities. That's just they are, okay, roughly speaking. However, while discussing the completeness property, it was mentioned that this is somewhat too advanced for this level. Actually, that is the property which is responsible for many of these things, which is behind these things, which in fact is behind everything in calculus. But that cannot be discussed right now, which is why you will see or not see proofs of many things. You have to take many things for granted. Only when you go from calculus to real analysis, there you will see all the proofs. So the statement of this intermediate value property is given as theorem 2 is just this. Let A and B be 2 points in an interval on which the function f is differentiable. Then f prime, that means the derivative of f, takes on every value between the derivative of f at a and the derivative of f at b. Okay, so if a function is differentiable in an interval and in that interval you take 2 points, then the derivative function takes on every value between its value at a and its value at b. So that is the intermediate value property of derivatives. And this means this actually has a consequence. This means that say you have a function g, okay, which takes two values at 2 points. Say at a it takes g of a and at b it takes g of b. I am not talking about derivatives, okay. G is just some function. A and b are 2 points in its domain, 2 distinct points of course, and you get these 2 values at these points. Now, if just for the sake of discussion, say g of a is smaller than g of b, so that the graph of g is like this. Say this is g of a and this is g of b, say. However, the function g is such that it does not take all the intermediate values. There is a gap. These values the function g does not take. Then, because of this lack of having the intermediate value property, g cannot be the derivative of some function f. G cannot be equal to f prime. That's what the authors said in the text. They wrote, so if a function does not show the intermediate value property in an interval, then it cannot be the derivative of a function in that interval. For example, if you consider the unit step function, let us recall that function by looking at its graph. And let me draw the graph there on that side. The unit step function takes only two values, 0 and 1. It mostly remains 0, but at one point at 0 suddenly it becomes 1 and then it remains 1. So the graph is just this. So this is our x-axis and this is the y-axis. To the left of the y-axis, the graph is just this, constantly 0. In other words, a part of the graph is the negative y-axis. At 0, however, the function has value 1, and that's why we make this circle black. And to the right of 0, the graph is this horizontal line. So the function becomes constantly 1 there. So this point is 0, 1, and this of course is 0. So this is the unit step function. The unit step function u of x doesn't have the intermediate value property. On R. R is itself is also an interval. It is this interval. So ux is not the derivative of a function in R. To see exactly how it does not satisfy the intermediate value property, it's very easy. You just take, say, these 2 points, -1 and 1. So if my interval is this, then in that interval I can choose any 2 points A and B. Say A is -1 and B is 1. What is u of -1? U of -1 is 0. U of 1, however, is 1. Now, if u really satisfied the intermediate value property, all the values between 0 and 1 should have been taken by u. However, that's not the case at all. For example, between u u of minus 1 and u of 1, you have the value 0.5. Does u take 0.5? No. It only takes 0 and 1 as its values. So that is why it's not satisfying the intermediate value property. And that is why by theorem 2, there exists no function f from R to R such that f is differentiable on R and f prime is equal to u. No such function exists. It's a very interesting question to seek a function if you are given a function like u, say, not u, some other function g. Does there exist a function f whose derivative is g? This is in the other direction. We are no longer trying to see whether g itself is differentiable. No. Does there exist a differentiable function whose derivative is g? This question leads us to the, it takes us towards integration. We are somewhat far away from that still. Okay, but the question has arisen here itself. And this is where this section ends and the exercises begin. So that's just it. The next calculus video, it won't be a video, it will be a community post containing solutions to some of the exercises. So that's just it for tonight. Tomorrow we have analysis. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.